Article 220.12b does not apply to feeder loads. Article 220.12b pertains to the calculation of lighting loads for branch circuits and feeders. It specifies that a minimum of 150 volt amps per 2 feet of outlet or strip length shall be included for each outlet. This requirement is intended to account for potential future additions or changes to the lighting system. Article 220.4b applies to the calculation of feeder loads and requires the use of the rating of the transformer supplying the feeder as the basis for the load calculation. This provision is based on the assumption that the transformer is the limiting factor in the capacity of the feeder. Therefore, when calculating feeder loads per NEC Article 220, Roman II, the rating of the transformer serving the feeder should be used as per Article 220.4b. Article 220.12b does not apply in this context. When calculating feeder loads, it is essential to understand the specific articles within the National Electrical Code, or NEC, that are relevant to the type of load being calculated. Feeders are conductors that carry power from the service equipment to a subpole or a branch circuit distribution point. The calculation of these loads ensures that the feeder conductors are adequately sized to handle the expected current without overheating, which could lead to insulation damage or fire. Article 220 of the NEC provides comprehensive guidelines for calculating branch circuit, feeder, and service loads. It's divided into several parts, each addressing different aspects of load calculation. Understanding the scope and application of each section is crucial for accurate and safe electrical installations. Article 220.12b specifically deals with lighting loads for branch circuits and feeders. It mandates a minimum volt-ampere allowance per unit length for certain types of lighting. However, this section is designed to address the general lighting needs and is not intended for calculating the total feeder load when a transformer is involved. The key provision to consider when dealing with a transformer-supplied feeder is Article 220.4b. This article states that the feeder load should be based on the transformer's rating. This is because the transformer itself is the source of power for the feeder, and its capacity dictates the maximum load that the feeder can handle. The transformer rating is typically expressed in kilovolt amperes, or kVA, and represents the apparent power that the transformer can supply. To calculate the feeder load, the kVA rating must be converted to amperes at the system voltage. The formula to convert kVA to amps for a three-phase system is amps equals kVA times 1000 divided by the square root of 3 times the voltage. For a single-phase system, the formula is amps equals kVA times 1000 divided by the voltage. This calculation provides the maximum current that the feeder must be capable of carrying. In addition to the transformer rating, other factors may influence the feeder load calculation. These include demand factors, diversity factors, and the type of loads connected to the feeder. Demand factors are multipliers applied to the total connected load to account for the fact that not all loads will operate simultaneously at their maximum rating. Diversity factors are similar but apply to multiple loads to account for the varying patterns of usage. The NEC provides tables and guidelines for applying these factors based on the occupancy type and the nature of the loads. For example, a commercial building may have different demand factors for lighting, receptacles, and HVAC equipment. When calculating the feeder load, it is important to consider all connected loads, including lighting, receptacles, motors, and other equipment. Each load should be assessed based on its volt-ampere rating or its rated current. The total load is then adjusted by any applicable demand or diversity factors. The resulting value is the calculated feeder load, which is used to determine the appropriate size of the feeder conductors and of current protection devices. In summary, when calculating feeder loads per NEC Article 220, Roman II, it is critical to focus on Article 220.4b, which directs you to use the transformer's rating as the basis for the calculation. Article 220.12b is not applicable in this context because it pertains to general lighting load calculations rather than the overall feeder load supplied by a transformer. By correctly applying these articles and considering all relevant factors, you can ensure that the feeder is adequately sized and protected, maintaining the safety and reliability of the electrical system. When undertaking feeder load calculations, several key steps should be followed to ensure accuracy and compliance with the National Electrical Code. Firstly, gather all necessary information about the electrical system, including the transformer rating, the voltage of the system, and the types and ratings of all connected loads. The transformer rating, typically found on the transformer's nameplate, is a crucial starting point for the calculation. The system voltage is also necessary to convert the kVA rating to amperes. Next, identify all connected loads and their respective volt-ampere ratings. This includes lighting, receptacles, motors, HVAC equipment, and any other electrical devices that will be supplied by the feeder. For motors, use the motor's nameplate's horsepower rating and convert it to volt-amperes using the appropriate conversion factors. Article 430 of the NEC provides detailed guidance on motor circuit calculations. Once all connected loads have been identified, determine whether any demand factors or diversity factors can be applied. Demand factors are multipliers that reduce the total calculated load based on the likelihood that not all loads will be operating simultaneously at their maximum rating. Diversity factors are similar but are applied to groups of loads to account for the varying patterns of usage. The NEC provides tables and guidelines for applying these factors based on the occupancy type and the nature of the loads. For example, a commercial building may have different demand factors for lighting, receptacles, and HVAC equipment. Apply the appropriate demand and diversity factors to the connected loads to calculate the adjusted load. This adjusted load represents the expected maximum load that the feeder will need to supply. Convert the transformer's kVA rating to amperes using the appropriate formula. For a three-phase system, use the formula amps equals kVA times 1000 divided by the square root of 3 times the voltage. For a single-phase system, use the formula amps equals kVA times 1000 divided by the voltage. This calculation provides the maximum current that the feeder must be capable of carrying based on the transformer's capacity. Compare the calculated feeder load, adjusted for demand and diversity factors, with the transformer's capacity in amperes. The feeder conductors and overcurrent protection devices must be sized to handle the larger of these two values. This ensures that the feeder is adequately protected against overloads and short circuits. Select the appropriate size feeder conductors based on the calculated load and the allowable ampacity of the conductors. The ampacity of a conductor is its current carrying capacity, which is determined by size, insulation type, and installation conditions. Article 310 of the NEC provides tables that list the ampacities of various conductors. Choose conductors that have an ampacity equal to or greater than the calculated feeder load. Select the appropriate size overcurrent protection devices, such as circuit breakers or fuses, to protect the feeder conductors against overloads and short circuits. The overcurrent protection devices must be sized to protect the conductors in accordance with Article 240 of the NEC. The size of the overcurrent protection devices should not exceed the ampacity of the conductors unless specifically permitted by the NEC. Document all calculations and assumptions made during the feeder load calculation process. This documentation should include the transformer rating, the connected loads, the demand and diversity factors applied, the calculated feeder load, and the selected conductor and overcurrent protection device sizes. Maintaining accurate documentation is essential for future reference and for demonstrating compliance with the NEC. Double-check all calculations and ensure that all applicable NEC requirements have been met. Review the calculations with a qualified electrical engineer or inspector to ensure accuracy and completeness. Making mistakes in feeder load calculations can have serious consequences, including overloaded conductors, damaged equipment, and potential fire hazards. By following these steps and paying close attention to detail, you can ensure that your feeder load calculations are accurate, safe, and compliant with the NEC. Additional considerations for feeder load calculations include accounting for voltage drop, harmonic currents, and future load growth. Voltage drop is the reduction in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for feeders and 5% for branch circuits. Harmonic currents are non-sinusoidal currents that can cause overheating and other problems in electrical systems. These currents are typically generated by electronic devices such as computers, variable frequency drives, and LED lighting. If harmonic currents are present, they must be accounted for in the feeder load calculation. Finally, it is important to consider future load growth when calculating feeder loads. The electrical system should be designed with sufficient capacity to accommodate future increases in load without requiring costly upgrades. A common practice is to add a safety factor of 25% to a calculated feeder load to account for future growth. Remember that the National Electrical Code is updated regularly, so it is essential to stay current with the latest edition. The NEC is a comprehensive set of rules and regulations designed to ensure the safety of electrical installations. By following the NEC and seeking guidance from qualified professionals, you can ensure that your feeder load calculations are accurate, safe, and compliant. Understanding the specific requirements of Article 220, particularly the distinction between Article 220.12b and Article 220.4b, is crucial for accurate feeder load calculations. Article 220.12b addresses the calculation of lighting loads for branch circuits and feeders, specifying a minimum volt-ampere allowance per unit length for certain types of lighting. However, this section is not intended for calculating the total feeder load when a transformer is involved. Article 220.4b is the key provision to consider when dealing with a transformer-supplied feeder. This article states that the feeder load should be based on the transformer's rating, as the transformer itself is the source of power for the feeder, and its capacity dictates the maximum load that the feeder can handle. In summary, when calculating feeder loads per NEC Article 220, Roman 2, it is critical to focus on Article 220.4b, which directs you to use the transformer's rating as the basis for the calculation. Article 220.12b is not applicable in this context because it pertains to general lighting load calculations rather than the overall feeder load supplied by a transformer. By correctly applying these articles and considering all relevant factors, you can ensure that the feeder is adequately sized and protected, maintaining the safety and reliability of the electrical system. Furthermore, it's important to remember that the NEC is a minimum standard. In some cases, it may be necessary to exceed the NEC requirements to ensure the reliability and performance of the electrical system. For example, if the feeder is supplying critical loads, such as life safety equipment or essential hospital services, it may be prudent to increase the feeder size and overcurrent protection to provide additional redundancy and reliability. Similarly, if the feeder is supplying sensitive electronic equipment, it may be necessary to install surge protection devices and harmonic filters to protect the equipment from voltage transients and harmonic distortion. In addition to the NEC, there may be local codes and regulations that apply to electrical installations. These local codes may be more stringent than the NEC and must be followed. It is important to consult with local authorities to determine the applicable codes and regulations. Feeder load calculations are a critical aspect of electrical design and installation. By following the NEC and seeking guidance from qualified professionals, you can ensure that your electrical systems are safe, reliable, and compliant with all applicable codes and regulations. Always prioritize safety and accuracy when working with electrical systems, and never hesitate to ask for help if you are unsure about any aspect of the calculation or installation process. Electrical work can be dangerous, and it is essential to take all necessary precautions to protect yourself and others from harm. Remember to energize circuits before working on them, use appropriate personal protective equipment, and follow all safety procedures. By adhering to these principles, you can ensure that your electrical projects are completed safely and successfully. The National Electrical Code serves as the cornerstone for safe electrical installations, and a thorough understanding of its articles, particularly those related to feeder load calculations, is essential for all electrical professionals.